Orbitals are where you can most likely find an electron. Or some people see it as the wave of an electron. It depends on how you view things. But basically, these guys come in different forms. What you've seen probably all your life is circles that go like that, right? Or if you get fancy, some of them go like this or like that. Yeah, guess what? Doesn't totally exist like that. Instead, what you have is orbitals that are in three-dimensional space because we live in a three-dimensional world. And what we have in these shells is just a little bit different than what you've seen as far as shapes are concerned. So what we have found over time is that there is a spherical type of orbital or shell where you will find the electrons. And we refer to this as the S shell, okay? Or that's actually technically a subshell. There are 3 different kinds of P subshells, and yes, they have like these figure 8 stuff, so they actually would fill in this general area, and again, that's where you're most likely to find an electron. In 3D space, it kind of looks like that, and electrons are flying all over the place. So there's a px, py, and pz. So we have one s. There are actually 3 p electrons. Now I can tell that I can't draw very well at all. I think you all can see that here. I'm not even going to attempt to draw the d orbitals. But many of them have a flower-like shape, and instead of having 2 spots, they'll have 4. And yes, it's actually possible for an electron to be kind of in all 4 at once. So I know that sort of bends reality maybe, but there are 5 d electrons. These are all subshells, or 5d subshells, I should say. Each of these can hold 2 electrons each. So if we have 2 electrons in the 1s, that means it can hold 2 electrons. And 2 electrons in each of the 3 p orbitals, that can hold 6 electrons. And in the there's 5d subshells, that means it can hold 10 electrons. Now keep in mind, we did not know how periodic trends were made or anything like that when we put together the periodic table. I love this part. What we find is that, guess what? There's 2 things over here. When you have a spot over here, that's filling an S block. Okay? There are 1, 2, 3, 4, 5, 6 over here, and that's what's filling p orbitals. D orbitals are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 perfectly, because these are filling d orbitals. And I'll show you what I mean about filling them, because this is something you have to sort of see before you understand what's going on. This would be filling f orbitals. There are 7 of them, hence why there's 14 things here. So we're going to go with some basic rules, and then I'm going to show you how to use that, okay? Here's what I'm going to say. Each block is representing where an electron can live, where its like home base is, okay? The period numbers help. So this 1, 2, 3, and 4 are going to help us build these things, okay? You only have 2 electrons in a subshell, just like we talked about. So S can hold 2, P can hold 6, D can hold 10, and no more. And when we fill things, we're going to fill it so that it's all spin up, or the little arrows are up, for the same subshell before pairing. What I mean by that is the p orbitals that have 6 things in it, we go all one direction and then we go all the other direction. It could be spin down first, it doesn't matter, okay? So let me show you what I mean and then try to explain it. So just as I said up here, sorry, the S block, see how this guy is really kind of considered over here? These 2 move back and forth just because they are so small. They do different stuff, okay? So I'm going to put an arrow in each of these boxes, and those are going to represent electrons, okay? And I'm going to try to find how many electrons and what the electron orbital configuration would be for calcium that's down here. Now, it says its number is 20, and as long as that's neutral, we should have 20 electrons in the end, okay? So let's see. I've got one here and one here. I'm going to start by filling this 1s block. I'll show you that I got this from, this is period 1, and I know that this comes from the S block because this is part of the S block. That's the end of that row. Just like you read, you go right down. This is the 2s. I know that because it's in the S block. 2s up, down. Now I move over here and I've got 1, 2, 3, 4, 5, 6. That's what I mean by you fill up first. 1, 2, 3, and then down. 4, 5, 6. I hope you can see that. Sorry, that's an up, down right there. Okay. Then we're done with that row. Now we come down to 3. Go up, down, and that's our 3s. 3p, 1, 2, 3, 4, 5, 6, up, 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 down, down, down. And finally, we have 2 more. Those are in the 4s. Okay. So this would be a way to write out all of the electrons, or we can put it in different terms. Okay. I could say instead, the 1s block has 2 electrons. See how I'm putting a 2 there and there's 2 electrons in there? That's all I'm doing here. 2s has 2 electrons. 2p has 6 electrons. 3s has 2 electrons. 3p has 6 electrons. And 4s has 2 electrons. Okay. A third way of writing that is to simplify it into what's known as the noble gas configuration. So I'm going to pull out a periodic table. Here is calcium. Oh, this is still too big. Here is calcium. See how that's 19 and 20? I want to go back and look at what was the last completed noble gas. That would be Ar. Okay? This is a shorthand way of saying, hey, everything that this noble gas had, because that completed its shell, the shell for shell number 3 is done at argon. If we say Ar, I have everything to that point, and then I have 2 more electrons. A way to write that as shorthand is to simply say, hey, I've got everything from argon. We put that in brackets. And in addition to having that, I'm going to have this too. It's just a way to speed things up and make it easier to see. Okay? Now the last way to represent this is with electron dots, or Lewis dots. So this kind of gives us a little preview, because see how this is Ar? Everything is complete up to that point. I look at the ones that have the number 4, and then I count up how many electrons are there. There's 2. And so I'm going to put Ca right here, and those 2 I represent as a dot. And you go north, east, southwest, north, east, southwest. So you could have up to 8 for this, and you shouldn't really have more. But that's something we will continue to work on. So that's another day altogether. Okay. As another example, why don't we try silicon? It's up here. Okay. So I'm going to fill 1, 2, 3, 4, 5, 6, 7. Oops. See how I'm doing that incorrectly? Good. Let me try that again. Si. 1, 2, 3, 4. Up, 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 down, down, down. That's what I've messed up before. I don't want to confuse you. up, down, and this would still be up, up. Okay. So I'm going to skip straight to the 1s2, 2s2 version, okay? So we have 1s2, 2s2, that's where this comes from, 2p6, 3s2, and 3p2. Since the noble gas up here, so this is silicon, the previous noble gas is neon, the noble gas configuration will be Ne, 3s2, 3p2. Okay. And the Lewis-Strauss structure for silicon, there are 4 electrons here. 1, 2, 3, 4. Good. Now I'm going to confuse you. And the only reason why I want to confuse you is because nature confuses us, and this is the way it goes. You see how we said this was 4s, right? This block right here, this row right here is 3d. Why? Because that's the way it works. We don't get to make those decisions. Okay? So let's try vanadium that's right here. Okay? So we're trying to get to right here. Okay? 1, 2, 3, 4. Up, 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 down, 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 up, down, up, 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 down, down, down. You're just following a nice pattern. Up, down, and then it's up, up, up. Okay? 1s2, 2s2, 2p6 right here, 3s2, 3p6, 4s2, 3d3. 1, 2, 3. You can write it this way. Technically, a lot of times you're supposed to put the S on the outside, but it doesn't matter for as far as this class is concerned. Okay, 2 more trends. Practice these, come back, pause it, try it again, practice them again, whatever you need to do. Just a couple more things. I want you to look at orbitals. Check out the electromagnetic spectrum. You've probably seen this before. There are different types of wavelengths of energy, and we will continue to talk about that in the next chapter. Okay. And then there's 2 trends that we didn't talk about. Ionization is basically how easily is it to pluck off an electron. When you have these things filled, they're pretty happy. Noble gases are called noble because they're like the royalty of all chemicals. And when you have like just a couple of electrons beyond that, so our first example, we're using calcium. He's happy up to here, and then he's got these 2 little electrons down here that are relatively easy to come off. They're relatively easy to come off because these want to sort of stay in the noble gas configuration. So these 2 out here can come off pretty easily. Ionization energy is how much energy it takes to remove an electron. Not all electrons are in the position to be the same. Okay, so that's what that means, okay? There's the last trend, and that is size. There is this cool thing that happens when you finally fill even a subshell or the entire row, like the entire period, where it's almost like the electrons come together and hug each other and pull each other tighter. Okay, so they're just like, hey, yeah, you're all here, right? And when they do that, they get smaller. And I know this sounds completely crazy, but as you go, like say this guy right here, once you put him on, or these 2, these are bigger than what you have as your noble gases, because basically everybody down to here is going, perfect, let's hug each other. And then there's the 2 lonesome guys that are kind of kicked out of that, and they just sort of roam way away from your nucleus. And so these are quite large in comparison to this guy, and it doesn't have to do necessarily with the atomic number. So check out those trends, see what you got. Thank you.